Hi class, we're going to take a look at a quick proof. Now for this proof, I'm going to start on the left hand side and I'm going to start with this portion here. So I'm going to let y equal to the sine inverse of x, and technically with domain of technically -1 to 1 and range of negative pi over 2 and pi over 2. Now, if you don't remember the sine inverse, what it looks like, I actually added it here. But when we construct the sine inverse, it comes from the sine function. And from the sine function, we're only looking at this step here. So your sine inverse looks like this. Oh, sorry, I was pointing out the wrong one. This is your sine. They're both kind of blue. And when you basically reverse all the coordinates, this is your resulting function. And technically, your sine inverse has domain of -1 to 1, which you can kind of see here, and range of negative pi over 2 to upper bound of pi over 2. So that's where we're going to start. And then this particular one, I'm going to start by saying that, well, I'm going to start on the left-hand side. So using the cosine of the sine inverse of x, this happens to be, since we already let y equal to cosine of x, so in this case, I'm just going to be replacing the sine inverse of x by technically my substitution here, and I'm letting just sine inverse be a regular y. So this is equal to a cosine of y. And at this point, we're kind of stuck in this position unless we start looking at identities. The identity that may help here is the identity of cosine squared of y plus sine squared of y is equal to 1. Or technically, by subtracting both sides of the equation, you're going to get cosine squared of y is equal to technically 1 minus sine squared of y. And if we take the square root, and I'm just going to look at the positive portion. So square root, there is a plus and minus, but for the proof, I just want to take a look at just the positive side. So we're looking at cosine of y. This is equal to the square root of 1 minus technically your sine squared of y. Now, at this point, we're a little bit stuck, but if we go back and use our original substitution, and you take the sine of both sides, so technically sine of y and sine inverse of x, they're gonna cancel, and you're gonna end up with sine of y is equal to x. This is by taking the sine of y, and on your right hand side, you're doing the sine of the sine inverse of x. So because they're inverse functions, these cancel, and then you're getting just the regular x. Now, what that allows us to do is that you could actually replace the cosine of y on our original proof, which is getting a little bit messy now because of the identities, as instead of having the cosine of y, I'm going to replace that by square root of 1 minus sine squared of x. So this is equivalent to the square root of 1 minus the sine squared technically of y. And this is equal to, if you squared both sides, well, you're gonna have, and let me just rewrite it here, that technically the sine squared of y is equal to x squared. So this is equivalent to the square root, and sine squared of y is equal to x squared. So 1 minus the x squared, which happens to be your right hand side. So at this point, this is the end of the proof. So we're actually done all the steps required. And remember that when you're doing a proof, you start with the left hand side and you're supposed to end up on the right hand side, or you could work on both portions and meet in the middle somewhere. At this point, what's required here is that you're basically declaring the sine inverse to be a variable. In this case, it works out very nicely with the y. Don't forget about domain and range. And then, well, a couple of evaluations, and we can actually see that the cosine of the sine inverse of x represents the square root of 1 minus x squared. There is supposed to be a plus and minus in here, except that for the proof, we don't really need it. That's already been taken care of here. Okay, that's actually it for this proof.